for joining us today for what really promises to be an exciting discussion about the future of space exploration. I'm your moderator today, Tariq J. Malik, Editor-in-Chief of Space.com, where, as of this week, we are 25 years old. We launched on the internet on July 20th of 1999 to bring you all the latest and greatest of space news and exploration. So I think that makes this our silver anniversary. And to celebrate, we thought it would be great to assemble an amazing group of scientists, of experts, of astronauts to look ahead at what the next 25 years of astronomy and spaceflight might look like, might bring to us all. And I can't wait to hear what they have to say. So I guess we should get to some introductions. So again, I'm the moderator here, Tariq Malik, and joining us for our virtual panel will be Dr. Sara Seager, exoplanet pioneer, astrophysicist, professor of planetary science, physics, and aeronautics and astronautics at MIT in Cambridge. Sara, welcome. Thanks for joining us today.
Thanks for having me.
And next up is Dr. John Mulchaey, director of the Carnegie Observatories. I think you're also deputy of science there too, right?
Yep.
Where you're building the Giant Magellan Telescope amongst your other observatories. Welcome, John. Thank you.
Thanks for having me.
And rounding out our panel today is Dr. Tom Marshburn, Chief Medical Officer for Sierra Space, where they're building the private Dream Chaser space plane, as well as the Life Habitat private space stations, and a former NASA astronaut, 3-time space flyer. And you just reminded me you flew on the shuttle, SpaceX's Dragon, and a Russian Soyuz. So that's like the hat trick of spacecraft right now. Welcome, Tom.
Hey, great to be here. Thanks very much.
Great. Well, I think a great place to start would be taking a look just of where we are right now in 2024, about like maybe what might be the biggest either advancement or milestone that you all have seen in your respective fields. I know it's kind of hard to pick one if it's even possible, but I thought that might be a fun place to start about what you think is the biggest thing to celebrate over the last quarter century. I don't know, Sara, would you like to start?
Yes, and I will just be very broad and say it's the birth and growth of the field of exoplanets. We now know of thousands of planets around nearby stars, and there have to be trillions of them in our galaxy alone. So just the fact moving that from science fiction to science fact is a momentous achievement of the last quarter century.
Great, and only more to come. I saw the recent count was much higher than I initially thought, 5,502
Wow.
as we speak. So, John, how about you?
For me, I think it's really the ability to probe the very early universe. Seeing the very, very first stars and galaxies in formation, and that's a field that's actively changing every day right now with James Webb Space Telescope, particularly. But it's super exciting. And 25 years ago, I was just out of grad school, and we only knew of objects that we could see maybe 10 billion years back in time, and now we're almost back to the Big Bang. So it's pretty exciting.
Wow. And of course, the project that you're leading are hoping to push that veil back a bit further too.
That's right. Yep. Hopefully.
Now, Tom, you've been to space and back several times, and I'm sure that the programs have changed over time for you too. Is there like a moment that is like the cathartic moment for you, or is it something that evolves over time?
It's something that evolves over time, and I'll cheat a little bit just as a preface to giving you an answer is to give you a few answers. That is, with human spaceflight, figuring out how humans can continue to live in space, 6 months up to a year. We're talking about bone muscle atrophy. I think that's one of the greatest things, that a barrier that we broke down that's going to enable us to spend years in space. Medical treatment, that's advanced discovery of the effects of space on the human body, particularly weightlessness, our eyes, our bones, our cardiovascular system, et cetera. But if I had to pick one thing, I'd have to say it's the discovery of how cytoskeletal structures change in weightlessness and the profound effects that has in DNA expression for those cells. So you change host pathogen interactions, you change how stem cells grow, how cancer cells grow. This has profound implications. We've already seen in some of the initial research on the ISS of how you can come up with drug interactions, you can come up with formulations for treatment one day in the very near future, treatment for neurodegenerative diseases and cancers. The list goes on. So I I think that discovery is going to have the most implications for healthcare on Earth, especially here in the next 5-10 years.
And you just reminded me, but 25 years ago in July of 1999, the International Space Station had 2 modules and no one permanently living on it. And here we are 25 years later, and it's continuous over time. So
continuous habitation. That's right. Continuously inhabited. That's right.
Great. Well, Sara, you kind of previewed, I think, this next question in your opening comments, but there weren't many exoplanets confirmed back in 1999. I think the first one or several was in 1992, right? With I think the poltergeist pulsar planets for there. And today we've got more than 5,502. Like I just mentioned, NASA just put out an announcement this week with that new number. And I'm curious for that research, that evolution to get to that point. Well, first of all, I know that you're looking for another Earth. Have we found that one yet? And if not, what's the biggest challenge there?
Well, the one thing I want everyone to appreciate too is that our solar system might be rare. We don't know how rare, but the reason why exoplanets is flourishing is there are all kinds of planets out there. So many planets that are so much easier to find. And so we want to think about another Earth. Right now, we're not able to find another Earth. Our Earth is so low mass, so small, so dim compared to our sun, that any counterpart would be equally hard to find. So right now we're fixated on Earth cousins, small planets orbiting small red dwarf stars, tiny stars with low luminosity that give off giant flares repeatedly. To find another Earth, we have to go to our next generation telescopes. And in particular, it's NASA's space-based plan for the Habitable Worlds Observatory, a telescope that would go above the blurring effects of Earth's atmosphere and would block out the starlight so we can see the planet light directly. But in the meantime, we have plenty to do with these Earth cousins instead of Earth twins.
Just a quick follow-up there, because I know that you were deeply involved with NASA's TESS, which mission was that found countless planets. Of course, we've seen Kepler. I know that you were looking on a concept study for Starshade too, as well. How has the technology improved in the ability to find these planets to the point where we've got kind of thousands that are confirmed and still looking for more? I mean, was there a key technology that made that possible that you rely on every day?
If I pick one, it's simply detectors. Mm-hmm. Like back in the so-called olden days, we didn't have CCDs, these relatively big surface area to make detections. You had what's called photomultiplier tube, where you could really only look at one star at a time. The ability to monitor tens of thousands, hundreds of thousands, even TESS is monitoring millions and millions of stars at a single time, and the sensitivity of the detector and the ability to develop and implement your detector the way you want, which wavelengths to favor, how deep the wells are, everything like that. It would be the detectors. But technology is always improving. Look at your phone. Could you have imagined 25 years ago that you'd have everything you need, right here, a great camera, great everything. So it's been a lot of technology. And part of it was just strategy, other than just technology. Just let me go into one little detail here. John may appreciate this. In astronomy, we used to always want to dither. You look at your object, switch to a standard star, switch back, switch around, switch here, switch there. And what people found for exoplanets, don't do that. Because your detector is very variable. If you could open your phone up and shine a light, like a laser or an LED, onto your pixel and move it around, it actually, the response, what comes back at you, varies a lot across a pixel, somewhat between pixels as well. So people want to just focus the telescope or keep that centroid of the star fixed on the same fraction of the pixel at all time, at least for transiting planets. So it was 1, detectors in general, and 2, strategy on how to use those detectors.
Wow. Should we even be looking for exoplanets to find an Earth twin anyway? I mean, you mentioned, I think before we started, that Venus is right in our neighborhood, the next planet down. I mean, is Venus the best candidate right now to find life as we know it on Earth?
There's so many things to do out there. Let's just say we all want to find an alien. We all want to meet that intelligent humanoid, and we sort of settle for less, right? We don't think we're going to find that. Well, we still have SETI going on strong, but what's our next kind of levels? Within our solar system, we know there's no, at least we are confident there's no advanced life of any kind. I mean, we know for sure there's no little green humanoids, but we don't know what kind of life is out there. And I think so many planets and so many moons are places where there could be life. And Venus is one, that's been around for a while. Carl Sagan, over half a century ago, proposed the idea that even though the surface is too hot for life, just like on Earth, as you go in a plane or hike up a mountain, it gets colder and colder, and so too on Venus. And he proposed maybe there's life in the clouds. 50 kilometers above the surface where it's the right temperature for life. And we have life on our clouds. So I'll try to sell you that idea, but the Venus clouds are not made of water. They're made of a nasty sulfuric acid. And we can talk a bit more about that. But I just want to say, in the solar system, it's like quality of data. We can go to another planet. We can bring a sample back in the future. We can send instruments there. For exoplanets, it's all remote sensing with telescopes. And there's always going to be some level of ambiguity there. But then we have quantity. So it's quality over quantity. We'd like to do everything.
Well, that's amazing. John, like Sara was talking about, these telescopes have been key to finding these exoplanets there. But 25 years ago, Hubble was fairly brand new. I think it was only like 9 years old or so. And Chandra, I think we were 3 days old. Space.com was when the Chandra Space X-ray telescope launched into orbit, and now ground-based telescopes, that reigned before seem to have a new future. Obviously you're building this ginormous Giant Magellan Telescope, which I think you're looking to come online in the 2030s or so, if everything comes out. And I'm wondering how GMT and the other giant telescopes like it, Europe's extremely large telescope, the 30-meter telescope in Hawaii, for example, could push those discoveries of other planets, of the deep universe, even forward over the next few decades there. Are we going to see the Big Bang, right? Is that it?
Well, we're never going to see the Big Bang, unfortunately, but we will see hopefully the first stars and galaxies, and that's pretty exciting. Telescope astronomy is all about collecting light, and you just heard about that from Sara. It's true with the exoplanets. It's true with everything, and so and that's where the bigger telescopes really help. We're trying to do really, really faint things. In fact, the other Earths around other stars, right? That is something that is really out of reach for the current telescopes, but future telescopes can do it. And on the ground, we can build big telescopes for a lot less money than we can in space. I mean, ideally, you do everything in space if you could, right? It's just very expensive and timely. And so, eventually, I do think astronomy will be primarily in space. I don't know if that'll be in 50 years or at some point as that technology improves and we can do that cheaper and faster and better. But for the moment, to build a telescope, the Giant Magellan Telescope is significantly larger than, for instance, James Webb. So, the Giant Magellan Telescope has 7 mirrors, each about 25 feet across, and James Webb is smaller than one of those mirrors. So the size of these telescopes is just enormous compared to the telescopes we have today. And so the light gathering power, the ability to see faint things is really incredible. And so while James Webb is helping us see some of those very first, galaxies and stars in the universe, to really understand them in detail, we're going to need to do spectroscopy, which requires a lot more light. And to do that, we really need the big telescope. So that's going to be very exciting. We're going to learn a lot of things when those telescopes come online.
I just want to interrupt with a very, very quick question, which hopefully has a brief answer. I love all the early universe work with the early galaxy work with the Webb, because it seems we're hearing that you've been finding that the galaxies are too big, they've evolved too quickly compared to models.
Yeah.
What out of that could the Giant Magellan Telescope help solve for us?
Yeah, I think that's a great question. So I do think that's the big surprise with James Webb is actually even prior to James Webb, we were starting to see that with Hubble, but James Webb was really confirmed. The universe got going really quickly, much more quickly than we understood, right? We're seeing, galaxies existing when we didn't think they did. We're seeing chemical enrichment. So this is another interesting thing, of course, because to have planets, we think you need these chemicals. You need, carbon, oxygen, all these things. And we're seeing that happened much earlier than we actually expected. So there's a lot of work to be done on the modeling side, but it's really true that this is where the big telescopes will allow us to study that in detail. So, the other issue with James Webb is it's an infrared telescope, which is great, right? That's an important wavelength region. But there are, of course, a lot of interesting features for certain elements, like oxygen particularly, that, of course, occur in the visible light range. And that's where these big telescopes will really help. So I think we're going to learn a lot about how those galaxies formed with that next generation of telescopes.
I didn't ask you to give an idea of the sheer scale. You kind of gave an initial thing about the mirrors and size, but I think GMT is what, about 30 meters across you're looking at? Is that right?
Yeah, it's about 20. It's 25, depending on how you measure it. It's about 25 meters across. Pretty substantial. Yeah.
So I mean that seems huge, and of course in Hawaii they're building the 30-meter telescope. Is there an upper limit for these giant telescopes on Earth that you see? I mean, I would assume that gravity eventually would win out, depending on how big you can build it.
Well, so interestingly enough, of course, the Europeans were trying to build a 100-meter, which then got scaled back to their EELT, which would be closer to 40, 39, I think, in the end. That is a challenge now that, once again, technology improves, things get better. A thing we're looking at Carnegie is actually distributed telescopes. The question is, do you need it to be a single structure, of course? And people will be familiar with interferometry. We use it in the radio all the time. We combine light from BLA or ALMA, people will be familiar with. That has not been terribly successful in the optical, but we believe technology is improving to the level where we may be able to do that in the visible light. And then that simplifies it if you don't need to have a single structure. But there's a lot of work to be done on that in the next decade or two. So it's exciting.
It's a really great question, because John and I are both lucky because in our careers, we can still use telescopes, or even the new telescopes that are in the same paradigm as almost all prior telescopes, just making a sweeping generalization. But there's going to come a time, at the 50th anniversary of this, you'll have to be having whole new paradigms of how to get to the next level in space and on the ground.
Oh, it's hard to even
read.
Wow. Tom, we've talked a lot about astronomy so far in our discussion today, but you're an astronaut, like we mentioned earlier, 3-time space flyer, and now chief medical officer at Sierra Space, where you're building commercial habitats like the Life habitat with stations like Orbital Reef, like a multi group project, and the Dream Chaser space plane, which I'm excited about, because not only is it a space plane for the 21st century, but the wings fold in. I mean, it looks like so sci-fi that's coming out. And I'm curious what role, and I think you've got some slides to share too, but I'm curious what role you see Sierra Space's private space station, private space vehicles, and the others like them. I mean, you've flown on one, SpaceX's Dragon, playing in the next 25 years of space travel.
Oh gosh, well, moving from the civil service side, I was an astronaut for NASA, into the commercial sector. That is clearly and essential to NASA's goal, is to go ahead and keep a low Earth orbit, and some aspects of getting to the moon, getting hardware into lunar orbit, cislunar as well, putting that into the private sector, hopefully making use of advanced innovation and agility and speed to make sure that we can continue everything we need to do in low Earth orbit to enable NASA to continue its exploration mission. And so at Sierra Space, and since I see the slides coming up, I'll just mention we have a vehicle that is slated at the end of the fourth quarter of this year to start bringing cargo up to the space station. Obviously, that's important for to have more than one route of one or two routes of getting cargo and access to the space station and access to space. To your point about it being a winged vehicle, hopefully an image will come up here soon. The winged vehicle itself allows you to re-enter with a much softer G profile, touchdown much softer as well. And I've ridden on the shuttle. I didn't even realize that I was in the mid deck. I didn't even realize we had touched down when we did with that nice landing. One thing we don't think about though is the opening shock of a parachute. When you come through on Soyuz or on Dragon, you got to get from that hypersonic to subsonic state. And that's with the drogue chute followed by a main chute. And those are the wildest parts of a space flight. If you like that kind of thing, it's the best ticket there is, right up there with the launch itself. But if you have delicate payloads you're bringing back, if you've got an ill or injured crew member, the Dream Chaser is definitely the way to go. So to answer your general question, absolutely, commercial space flight, the space stations, access to space, commercial is an essential way to go. It remains to be seen how it's going to all play out, but we're going to be a part of that whole process.
What about like some other uses? Because like NASA is using commercial vehicles like Dream Chaser, like Dragon to fly crew like a Boeing Starliner, which is being tested right now. I mean, is there a future in the next couple of decades where you could see a Sierra Space built, owned, operated like moon base that you're renting out time to NASA, to the agencies of the world, to researchers like John and his other astronomers, or Sarah, looking for strange new worlds out there?
Yeah, I mean, we're starting with low Earth orbit. We're committed to having a destination. If we get it up, eventually the picture of our inflatable habitat, life habitat, which we've been testing with burst tests, stronger than steel. It's really impressive. Huge place to start building your laboratories, your research facilities, to take advantage of a lot of those things I was talking about. Crystalline solids like your semiconductors, your glasses, and of course the biology work we were talking about. So you can actually begin manufacturing in space, providing a research facility, not just human research, but materials as well. And then finally, opening access to space. Tourism is not one of our prime goals for our space stations, but it could certainly be a part of it. So in one launch, we can put up 1/3 the living space of the International Space Station in just one launch, with the soft goods and the ability to expand once you get into space, into a larger living area. So, but several companies are coming together to provide this kind of destination, or a destination for low Earth orbit, so that fulfill the goals of NASA, to fulfill the goals of private industry and of human endeavor to get into low Earth orbit. And to your point, all of this is, particularly our soft goods habitats, are extendable to get into lunar orbit and to have habitats on the lunar surface, to include ways of getting out of your landing vehicle into that habitat. So tunnels, so we can begin to develop a space base. So all of these things are kind of coming together. We build satellites as well, and be able to increase our communications and our cybersecurity, both in lunar orbit and cislunar and Earth, and eventually to Mars.
I just want to say that. Can I add
Go
something?
Go ahead, Sarah.
We are definitely in sciences, trying to go with that phrase, all ships rise with the rising tide, and to take advantage of some of the new capabilities presented to us. Like, I do work with perhaps like a competitor of Tom's, Max Space, who have a different kind of inflatable. And we work with them, not on inflatables, but their same technology for our next potential balloon mission to Venus. In their case, it's like an inflatable with these cords that are super strong and provide the structure. So we have that. We have this, I don't know if you've, so we work with Rocket Lab, who are the leaders of our first largely privately funded mission to Venus. Because you can be small and flexible. And we're trying to change the way we do space science. That's more reminiscent of these companies like Sierra Space and others that are innovative, that are taking risks, that can launch frequently with small focused missions, rather than waiting like we have for Venus for over 4 decades to go back to the Venus atmosphere.
That was actually my next big question. So it was for you and for John, like what opportunity you see there. By the way, I personally feel that Venus hasn't gotten enough love over the last few decades, so it is exciting to hear about that mission that you're working with Rocket Lab on, and of course I think you've got the Venus Cloud Life initiative too. But I guess the initial question that I had for the two of you was what private spaceflight could mean, like in space, for researchers. Like, could there be like a private exoplanet atmosphere observatory at L2, or some sort of commercial observatory that you could put some racks in, or observatory equipment in, John? But this whole mission concept thing was not something that I was thinking about, Sarah, when I was
it's going to take a lot of effort to change, like once you do things a certain way, even you, like on a daily basis, it would take a lot of effort to uproot and change. But the way that astronomy is working now, there's room for a complementary new way. Like John and I, we're really fully, the astronomy community has the decadal survey. Planetary has that now too. And typically it's for a big mission that couldn't be privately funded. Like NASA's Habitable Worlds Observatory will launch in the 2040s, very long time from now. And it will serve a large fraction of the community. but we still see so much room for small focused missions. But we'd have to get, you can't just like, wow, pull out of the hat private funding. We'd have to get the community on board, NASA, NSF on board to want to do smaller focused missions. But when you look at a company like who I have my eye on now, Firefly, have you been watching how they have this super fast turnaround? So you're not waiting 10 or 20 years to get your mission, but you're doing it really right away, like opportunistic. And we're just waiting for these commercial spaceflight companies to, like Rocket Lab is aiming to go interplanetary, so we can do a lot of small focused missions like that. And it could be a huge game changer instead of waiting 20, 30, 40 years for your mission to have lots of frequent small missions that build on each other. Or if you dead end, they go off in a new direction.
And I'll have to add to that, in the commercial sector, developing devices that support telescopes, provide stability, provide the communications back, all of the pointing, et cetera. GNC. These are some things that Sierra Space builds. And when you're able to do it, have innovation and be able to build it more, mass produce it and make it cheaper, then that helps everyone as well. So there's a lot of cross-pollination.
Yeah, I'll give you an example. I had my own space telescope. Actually, it was a JPL implemented, MIT JPL, tiny CubeSat. We called it Asteria. Its goal was to demonstrate precision pointing in a small package. We dream of a constellation. That's bad because astronomers, we hate constellations, right? We want a constellation of small telescopes that can point precisely. Remember, I told you need the centroid of your star on the same like 1/100th, 1/1000th of a pixel at all times. But each of these telescopes would focus on a bright sun-like star. They're spread all around the sky, so one big telescope doesn't help. And we'd have a few hundred of these, each looking for a transiting Earth if it exists. But the point relevant here that we can't do that because the unit cost is like literally astronomical in our paradigm. And so we are having to wait for this mass production, what Tom just said, how can we're waiting for the cost to go down per unit and for us to figure out how to mesh in more of the way that commercial is doing.
John, do you see opportunity in terms of like the use of commercial facilities in space for the types of research that you're hoping to do with GMT, with the other observatories that self? I mean, is there room for the commercial folks to build that sort of a one size fits all for researchers like yourself to partake of, or are they truly so specialized that they have to be one-offs?
Well, yeah, I mean, I think it's a good question. I mean, I think it will happen eventually. At some point, this will become cheap enough that that's the route we're going to take. Like I said, at some point, we're going to be in space pretty much all the time, I suspect. But I actually go with Sarah. I actually think that smaller missions that are more focused is a smart strategy, because the problem now is the big facilities like GMT or James Webb, where people will know it's it's a $10 billion facility. That's exceptionally expensive. Now, James Webb serves a wide variety of science. It's being used by many. I think it's worth every penny of that $10 billion personally. But the problem is when you have missions like that, it doesn't leave a lot of money for other missions. So I spent a lot of my career doing X-ray astronomy, Chandra. I've worked on Chandra for many years. What's the next thing to do in the X-ray space? That X-ray community needs a telescope, but do we have the billions of dollars to do it? And so one way around that is to do things that are a little more focused. Right? Chandra does a lot of different things. Hubble, James Webb, they do have many different functions. Something more like Kepler and TESS, which were very focused on the scientific problem, I think you can get a lot of bang for the buck. And so I do think that's the future. And that is where these companies really could play a big role once we get it to a place where we can kind of uniformly, regularly use them for focused projects.
I love this. So you're saying there's room in the X-ray community to have some smaller focused missions, but they still have large enough collecting area and can still nail something. That's great.
Yeah, I do. So it's something we've been talking about. And I think the problem is, you mentioned this earlier, Sarah, we're used to doing things a certain way. We've been doing, ground-based astronomy, we've been for 120, 140 years or something. We've been bigger, right? In a kind of a standard way without thinking a little bit outside the box. I do think that the current generation of big giant telescopes we're building is the last like those. Like, I do feel we're going to need a paradigm shift. And it's similar in those communities. The X-ray community has always had, we had Chandra was our thing after we had ROSAT in these previous missions. We're going to probably have to do things that are a little more focused and cheaper, and you just do multiple, And if the technology gets cheap enough, you can also be a little riskier, right? You can try things. When you spend the reason James Webb was $10 billion is because it really had to work. It is a lot of very complicated things. but there were so many checks and balances to make sure it actually worked. If it had been 200 million, which it's still a lot of money to many people, but in space terms it's not, maybe you would have done it faster, or taken more risks. And so I do think that that's kind of the future at some point.
Yeah, we still want NASA and others to invest in the very large things.
You need the big things.
Complementary way to do things more frequently and more focused.
That's right.
I had a question that I'm curious if it ties both the commercial side of the work that Tom is doing, the astronaut work, Tom, that you did when you were on the space station, with the sort of research needs that John, Sarah, you and your teams are looking to pursue in the future. And I guess the question there is there a need or a role to have these vast new commercial facilities in space, a new space station with, like, say, telescopes on it, where you would have human-tended science out there? Is it an exoplanet observatory that has a team there in space overseeing it, or John, as you mentioned, a more affordable telescope, but you've got a team of scientists that can upgrade it while they're there, or turn it, pivot it in real time. And it sounds easy when I think about it, because it sounds very sci-fi. But Tom, you were the astronaut that were doing science on the space station, as your job, and I'm sure it's a lot more complicated to have human-tended science in space there. And I'm curious what the future could be and what uses, Sarah, John, you could see there for it.
Yeah, I'll just preface it with saying, generally speaking, in astronomy, I think we were talking about before, I think the general feeling is whatever you do, don't let an astronaut get close to the telescope. So the alpha magnetic spectrometer on board the ISS, I never had direct contact with it. I did spacewalks and came near it, but we did have to have some astronauts do some work on it to replace carbon dioxide pump. And obviously Hubble, we had repair missions to that as well. But I imagine that either we have one of these big expensive projects out at the Lagrangian point, and we'll have to figure out, is it worthwhile? If there's a failure, is it going to be worthwhile to send a mission there? From an astronaut's perspective, that's a primo mission. Everyone would want to do it. Every aspect of space flight for humans is very exciting in that regard. But probably more realistic is going to be commercial companies establishing a platform, either on the moon, lunar orbit, even low Earth orbit, so that some of these smaller missions can come up and just stick it on a platform. So we supply the power, we supply the stability, for instance, and find out and give whatever astronomers need. So when they fly their telescopes up, we can plug it in for them.
There's a lot of
my thinking.
In terms of traditional astronomy, most wavelengths, Earth is bad for astronomy.
Right.
You want to get away as far away from Earth as possible. It's hot, it's bright, the orbit takes you into Earth's shadow 30 minutes every hour and a half. So we want to get as far away as possible. But that doesn't mean there's still a lot of other science we can do. Earth observing, maybe a launching pad, go to another planet and things like that. But is that all true for X-ray, John? Or is it okay? Low Earth orbit's okay for X-ray astronomy?
No, it has similar problems too. I mean, you have to worry about, electric particles and things like that cause all sorts of problems. I guess my question really is, though, how much of a human, do you really need the human so much in the future, or is robotics and technology going to replace that a lot? And my guess is the answer is probably yes. But that now I'm really out of my field of expertise, and maybe Tom has some ideas there. But
I would just say in general, there's always a discussion of robotics versus humans, and clearly robotics are the vanguard. They're that's the way we start. And then we find out if there's a use case for a human being there, much like going to Mars. Robots essentially have mapped out the planet, and there's more to do in that regard to find out if we're going to send humans, where should they go? Where can we get the maximum benefit for the human arriving there? So I see it as a melding of the two, not competition really. And regardless if humans are there, it's going to be robotics assisted, no question about it.
Well, I would say if there is a robot wrangler position in space for any of these, I would probably want to apply. I mean, I love you all out there, space fans, but if that's a job where I can internet, I might have to take that up. So, well, speaking of robots, and Sarah, I think this might be great to start with you. The idea of like AI systems, artificial intelligence systems, seemed a lot more like science fiction back in '99 when we started. Then it seems like today. I think there's like a chatbot in my phone that I can talk to when I'm lonely if I want to. And I'm curious, what role that you and John and Tom, what role do you see AI playing in the future of astronomy and of spaceflight? Because it seems like there's so much data, having that technology can be a boon, but if it makes mistakes, then maybe it's not as helpful as it could be. I don't know, Sarah, is there anything that you've been thinking about on that front, how it could help exoplanet research and that
Well,
search?
to be honest, we're still waiting for the magic bullet that we all think AI is for exoplanets. There's really two categories. The one more mundane one is, as you said, it makes things faster and more robust. So we want to find planets. We can train AI to look through all of our test data, the millions of stars or what have you, and it can perhaps find things more reliably or find things humans or our algorithms would overlook. But what we really want AI to do is what it does in other fields, where it finds something humans couldn't do. So it's not just doing it faster, more reliably, but it's finding something we can't do by putting information together that we cannot. And it has occasionally found a planet, maybe once or twice, by putting random things together, seemingly, that in that sense. Right now, it does play a role. And if I may just go into a tiny bit of detail in case anyone out there really loves this stuff, that,
No, please do.
for exoplanets, we have such limited data and we try to make massively complex inferences. So if you hear about a lava world or a water world, honestly, a lot of steps had to happen between the data we got, the models we matched, and our inference. So one of the things is that because we're kind of data starved, our models, they benefit from AI. It kind of fills in parameter space for us in a way that's really helpful. That was maybe a bit of an overview for it. So it plays a role in kind of modeling, but I haven't yet seen it do this magic bullet, but I'm still looking for it.
John, how about you?
Yeah, no, I think that was a really great description of where we're at. We all know it's coming for the field, but it just hasn't hit yet. I mean, it hasn't hit for, I think, the reason Sarah just mentioned. Every astronomy department in the world is, how do we do an AI center? How do we, but nobody has really demonstrated yet, because I think it is that capability. It needs to be able to do things that we can't do. That said, there is a lot of data, and it is helpful to have, something that can go through and find patterns. And so it's being used in that way, but I don't think it's yet hit that really high point that it will in the future. But everybody's thinking about it. But as far as I would agree with Sarah, I don't really think it's hit the mark yet in astronomy, but it will at some point. The question is just when.
I just want to tell John one interesting thing he might appreciate. So one of the things when we want to search for transiting planets, I mean, we think we have a lot, right? You said we have 5,000 planets. A large majority of those are transiting. It's not enough for supervised learning. You need tens of thousands of hits, right? And so one thing we try to do is make fake transits. But this is the point I think John's going to love. It turns out it's very, very hard, nearly impossible to simulate noise accurately enough so it's real noise. So when you want to create noise, like telescope noise, it's really hard to do. And that's what would prevent you from doing the training.
It's I love that story. Let me just say, because it's funny, because I often say, to me, exoplanets is really the hottest field in astronomy. I think there's no question about it. To me, it is, and I don't work on it. But I do think it's the most interesting thing. I talk about it all the time at a very low level. But I think one thing I'm learning from talking to people who are experts in exoplanets is just how immature the field really is. I think that's what you're saying here. It's at such an early stage. We have to remember it basically the field didn't really exist 25 years ago, or barely existed 25 years ago. There's so much growth potential in this field. And, we've been studying galaxies 100 years ago, Edwin Hubble showed that Andromeda was a galaxy, right? So it's been a long time. We probably run our course, but I don't know.
I think John and I need to get together, because you know what? I've been watching with envy all of the galaxies work with the James Webb, because think about it this way. They got James Webb. They thought they knew what they were going to find, and boom, they're so surprised that these galaxies are way bigger. They evolve faster. It's like if you had a baby and it was suddenly an adult. They just grew. Enrichment meant they grew and the stars exploded and new stars formed, all in the time they didn't expect. So to me, that's what I've got my eye on that field as being one of the
there you go. So everybody always finds it's when you know too much about your own field, all the ups and downs. And so I think it's a lot. Sometimes everything on the outside sounds even more interesting.
I'll tell you what.
reality.
Yeah, one of my favorite stories, a little bit tangent to this topic, but it's kind of speaking a little bit to what you're talking about, Tariq, is I, as a physician, I like to give talks, benefits of spaceflight astronomy, all this, why are we doing all this for humankind? And I love the subset of what you're talking about, how Hubble, particularly Hubble, image processing has aided MRI, CT scan imaging to improve outputs and detection in that. And so I would love to know what, to keep in touch and find out what happens with if image processing is an aspect that AI can assist, to see what it does for medical care, because so much of our diagnosis is imaging, and there's a direct correlation to that.
Well, I hadn't thought about medical care in space, but I could definitely see like an AI thing for there. I did want to ask about spaceflight though, and AI because of a couple of things. Number one, I'm curious. Tony Stark has Jarvis, right, to help him design his new Iron Man suits or whatever. And I'm curious if you see at Sierra Space a role there to either design, test, iterate future types of vehicles that you might need or systems on habitats, on bases. And then as a medical doctor who's flown in space, and with there are plans to send people to Mars, the moon for long periods of time where they might be a bit more isolated. I know there have been a lot of tests on the space station to use AI-driven robots to be a companion or whatnot, and I'm curious if there is a role there that you see that we haven't filled yet, to help keep astronauts just calm and happy and on their way.
Yeah, people are looking into each one of those aspects. The last one you described is probably the hardest nut to crack, to convince a human being that some computer-generated conversation, noise, face, whatever is real enough to be able to accomplish what you said, to calm down an astronaut. But to your point, the AI, already we're using our company AI, a subset of it, to do searches through our database and through our tools, through our data, to help inform us, not to take the place of, that doesn't make sense, but to inform us when it comes to design, say, hey, maybe there's something we hadn't thought of, which is what it does for those who write and for artists, et cetera. What we've talked about with NASA in particular, and been thinking about for exploration, bringing some sort of AI capability. It's been shown in emergency rooms, hospitals around the world that, yes, literature is out there to support your data. AI is not going to generate new data. However, getting through that literature could take an hour or more, and you have to make an immediate decision. It's pretty impressive what AI can do, just to even go into the medical literature and say, here's the next step, and here's the chances it's going to work, and here are the complications, and here's your error spread, because human studies are generally not that good, so kind of present a Cochrane analysis type of error spread. So at least the physician or the practitioner can just look at this and go, okay, this makes sense. I can say that I've looked at the latest literature and I'm making the best decision possible on that. And that applies to medical care in space. We're going to have, luminal speed's going to prevent us from having any real-time consultation with a medical care practitioner on the ground or with the mission control. So maximizing capability of the data that we have on board, which can be uploaded, and that doesn't have to be real-time, but once you got the cache of data, being able to sift through that to make a real-time decision, I think is going to play an important role.
Well, I do have another kind of sci-fi follow-up to that, and this one is mostly, I think, Sarah and John, for you, because we talked a lot about the astronomy that you could do, the types of depths, I guess, in the universe that bigger and better and more capable instruments will be able to do. But I'm very curious about the search for first, Eddie, for those technosignatures, for those signs of other intelligence that are out there. I know it seems fairly fresh in the last like decade or so, in terms of the actual active awareness in the public side, at least, to look for those things. But I'm curious if there are new technologies, new efforts that we've been talking about that would be really apt in the search for those types of signatures, to see if they are in fact out there, and if finding something that we can confirm would change, I guess, life as we know it on Earth, if we can find an actual technosignature from space. I'm just curious if it's a sign of limited tech right now, or if there's something that we can just build to achieve that.
For astronomy, we just need bigger collecting area. That's a sort of nice general answer, but I do want to put in a plug for technosignatures, because what's been happening in exoplanets as we're studying more and more exoplanet atmospheres, it's starting to dawn on us just how hard it's going to be to robustly find a sign of life by biosignature gases. That's a gas that is produced by life that can accumulate in the atmosphere to detectable levels. Like on our Earth, we have oxygen that fills our atmosphere to 20% by volume, but without plants and photosynthetic bacteria, we'd have no oxygen. But for every biosignature gas, astronomers can come up with a list of false positives, ways to make it without life. And it's getting tricky, actually. And this is like a whole other topic, but the phosphine on Venus discovery I was a part of is incredibly controversial. And that's for a planet right next door that supposedly we know way more about than we'll ever know about an exoplanet.
Or what's making the methane on Mars.
Methane on Mars, yes. And so there's a lot of skepticism about the detection at all, and then interpretation. So there is this growth. It's not going to take over biosignature, but it's going to be complementary. Are there any signals that we can be sure that are robust? And so I think the field is still finding its way, but whether these are gases, like there's this gas sulfur hexafluoride. I mean, life doesn't want to use fluorine, and we use that in industry. There's gases, there's other large structures, but arguably all of them, each of them would require much more collection area than we have.
And I guess it assumes that we would recognize any of those types of signatures, right? For what they are.
I think that's the biggest challenge. That when people ask me that question, that's exactly my response. Is we always look for the things that we're doing. That's how the history of our field has always been. We sent out radio waves, so let's look for radio waves. The question is, would you even recognize a signature for life? However, I think it's absolutely important that people are doing it, because it would be obviously a tremendous discovery. And as Sara said, that would be the one way you would really be sure. Yeah. If you actually, could communicate with somebody, then you would know that you've actually done it. It's hard to that will be a very interesting day for humans.
That probably will come back to your first question, Tariq. For all of spaceflight, whether it's astronomy or human spaceflight, all of our interest, finding life elsewhere could be the number one thing that changes human culture as much as anything.
Yeah. Man, well, actually, I have a follow-up to that, because I would imagine that if we found any kind of life, even if it's like a lichen somewhere in a cave on Mars, we would have to figure out how we're going to treat that, and what we're going to do when we go there. And I'm curious if you, all for your respective fields, for astronomy, for spaceflight, if you see a need or a requirement even for the types of ethical frameworks that we would have to approach to go. It's kind of like a heady question. I apologize, but as I look to the future in space exploration, and I see players like yourself, Tom, in Sierra Space, where you're building your own space destinations. We've got companies that are hoping to drill into the moon with commercial moon rovers, that sort of thing too. And I'm wondering if it's time for a new type of framework. In 1967, there was the Peaceful Outer Uses of Space Treaty with the UN, and I'm curious if you see a need for something similar to that would be a bit more expansive to the fields that we now have that we didn't back when the space age was brand new, or even 25 years ago. Do you see a need for that? How on the spaceflight side, companies and nations interact, Tom, or Sara and John, about the sharing of the knowledge that people are collecting, that your scientists are discovering? An example of that that came to me recently was China's samples of the moon that they are sharing across from their first far side, or their first sample return mission. That was really great to see that sharing go on, because they were the first samples to be shared there. But do we need a new framework for the next 25 years, for the next 50 years, to ensure that there's that cross-pollination of research, of behavior in orbit?
I'll just start, because there's very clearly some implications for human spaceflight, in particular when it comes to providing access to space. What is fair? What is how should we approach that? But one thing that I found very heartening, particularly when it comes to human spaceflight, the various companies that are want to populate low Earth orbit and the moon, we're just at the seed stages, the nation stages of robust communication between medical groups, so that anything that happens in one company can get communicated out, so it's not repeated in another company. I feel that's an important ethical situation that we are addressing. Sometimes in the medical community, we call ourselves competimates in a sense, because there is an intent to do the right thing in that regard. And then finally, when it comes to human space flight, access to wherever you are, low Earth orbit or whatever, and returning people safely, making sure if we are able to develop a special rescue scenario, how is that handled, so to speak. So I think that's and I would like to add to your question for John and Sarah when it comes to astronomy in general and near Earth asteroids and something heading for the Earth, and figuring out what do we do about it, who's affected about it, and how do we change that.
That's a really good question there too. I don't know, John, Sarah, did you have thoughts about that, or is it because of the nature of astronomy? Is it pretty clear cut on how researchers need to approach it in the next 20 years?
Just to address Tom's question briefly, we like to believe anything bright enough, anything big enough to hurt of, we'll see it in time. Hurt us, we will see in time. And we've had the DART mission that was able to move one. But we definitely need some kind of international plan to be moving on that. One thought that kind of crossed my mind, it's too detailed to get into here, but the people who push the boundaries and make things happen and change the world, they're rarely people who are cooperative and want to agree on being nice. So we do have to take personal responsibility, though. So a question that I get asked a lot in my Morningstar missions to Venus, we call our international collaboration, international consortium. What about planetary protection? We don't want to go to a planet and mess it up. So we will definitely adhere to whatever the best practices are right now. We are definitely going to be sharing our data, our minimal, very tiny amount of data we're going to get from our first mission to Venus and the missions going forward. But there is a level of personal responsibility that we have to encourage people to maintain, because as you said in your question, there really are no rules.
Wow. So, but I was looking at the clock here, and it looks like we're in like our last 10 minutes that we've got for our discussion. So I did want to spend a bit of time looking ahead at the end, as if the next 25 years are over. It's 2049 right now, and we're having our 50th anniversary talk. What mystery or capability or milestone do you want to see solved by that year 2049, at the end of the next 25 years? If there's one, there could be more, there could be multiple ones. I've got like a laundry list of what I want to see happen in the next 25 years. But I don't know, Sarah, if you want to start, or we could go around, whoever has the first.
I'll start. I was just trying to figure out how old I'm going to be. I will probably be, I will be almost 80, and I will be doing everything in my power between now and then to solve the mystery I hope is solved, and that is, are there other Earths nearby? Earth twins we're talking about, planets like Earth that are about the same size and mass, orbiting a true sun-like star, that have evidence of water oceans and thin atmospheres of the kind that can and might support life.
Oh, that's a great one. John, how about you?
Yeah, I think that is in all of astronomy, that is the biggest question. But I think we'll hopefully have some understanding of how the early universe worked, why galaxies form so quickly. I think we'll probably know that hopefully within 10 years. And we still have the mystery. We still don't understand what 96% of the universe is in dark matter and dark energy, and that's pretty troubling. And so we're spending a lot of time on experiments. It's a topic we haven't even talked about here, trying to understand if we can make any progress on that field, because it feels like, certainly with dark matter, we haven't made a lot of progress, and it's getting to the point where it's becoming, I'd say, very concerning. You'd like to know what the universe is made of.
So there's not like a dark energy or dark matter glasses that you can put on to finally filter all that out so you can finally see it, right?
Well, no. So the question is, can you design experiments to really make progress on these fields? And we are designing those experiments, but I'd say, if you had asked Vera Rubin in 1970 whether, there would be an answer for dark matter in 2024, she would have almost said certainly. Surprising that here we are this long after and still don't know what it is.
And Tom, I'm going to come to you real quick, but I did want to ask Sarah about like finding another Earth. There's like some other kind of crazy ideas out there that to send missions to like Alpha Centauri with like tiny little chips to go on out there. Could like a mission like that answer that question in the next 25 years, or do we need like true big interstellar ships that we're gonna have to wait or find some other big breakthrough in propulsion to get out there to find them? Or is it just a matter of building better detectors that you were saying?
No, if we definitely want to get a more close-up view, either with sending, this idea of starshot, thousands of tiny space chips, but we have to be lucky because we can't send them to every planet we know. We have to send them in a certain direction and they're going to swing by the planet. It probably won't happen in 25 years unless we had a ginormous injection of cash, because we still have to develop the technology, launch them, and it would take 20 years to get there. So that is still ways away. And there are a couple of other ideas in that space as well. So that might be perhaps for the 75th anniversary of space.com.
My clock is ticking for sure. Tom, I think you get to have the final word on the predictions from the future. What do you hope to see in 2049, either solved or achieved, or just like a nice fact that isn't on the drawing board for the next 20 years?
Well, I have to say, not on the drawing board is where I think we're all wanting to go in the next several hundred years, perhaps. And it's all starting with John, Sara, and their colleagues' work. And that is a single planet entity is doomed to extinction. So we're going to have to figure out another place to go and go there. However, all the innovation that comes from that, the inspiration that comes from that, as we find out more about the origins of the universe and about the potential or the actual existence of life elsewhere, that will continue to feed what we're doing right now towards that goal. And ultimately, tracking back to 25 years from now, humans going to Mars, humans living on the moon, humans having a robust, established manufacturing base in low Earth orbit, so the whole commercial industry can feed itself and not reliant on a government agency anymore. And so, and then maximizing the return on that for improving life on Earth, because that'll establish the cycle that'll just keep everything going and having improvements for everyone.
Oh, that's amazing. I think chief on my list 25 years ago was that there wouldn't just be one or two different spacecraft, that there'd be like a whole different fleet. I think we're kind of there now, it seems like, and there's so many different ways to get into space, so many different missions and space telescopes that are finding all of these strange new worlds. So I guess in 2049, I'd like to still be writing about space. So I'm gonna put that there. That's my pin for my prediction. But I would like to be doing it from the moon, maybe, if that's a little more ambitious. So.
One thing I'd like to say, just a quick sentence, and that is one of the best benefits, probably 25 years from now, when we look back on all of our work, cooperative international discovery, which is what astronomy is, which is what human spaceflight is, as a platform for peaceful society. That might end up being the greatest thing that we've achieved. And looking back, hopefully in 25 years, we'll start to see that.
Great. Well, hopefully in 2049, we will definitely be doing so. Well, I feel like we could just keep going forever, but unfortunately our time is up. So let's hope we'll write these predictions down, and then I'll reach out to everybody in 25 years, and we'll see how accurate we were. But thank you so much, Sara, John, Tom, for your time today to kind of take a look at the last 25 years, of the next 25 years, and what may be on the horizon. I really do appreciate it. And to everyone out there watching, thank you also, not just for your time today for this panel, but for your ongoing readership and dedication and your passion for 25 years of amazing space exploration with space.com. I can't appreciate it enough and say thank you enough for that. I've been your moderator and your host, Tariq Malik with space.com. Thank you all again, and have a great day, and keep looking up, because big things are to come, as we learned today. So thank you all, and have a